Our story begins with a vast cloud of gas and dust floating silently in the cosmic void.
This immense cloud was known as the Solar Nebula, a swirling disk of gas and dust that would eventually give birth to our solar system. It was within this nebula that the early stages of our solar system's formation began to unfold. The nebula was primarily composed of hydrogen and helium, the two lightest and most abundant elements in the universe. However, it also contained heavier elements, remnants from long-dead stars that had exploded in supernovae, scattering their enriched guts across the cosmos.
These heavier elements, such as carbon, oxygen, and iron, were the essential building blocks for the formation of planets and other celestial bodies. Initially, the nebula was cold and dark, a seemingly lifeless expanse drifting through the vastness of space. It drifted aimlessly, a silent witness to the universe's grand tapestry. But then, gravity began to exert its influence, pulling the gas and dust together, initiating a slow but inevitable collapse.
As the cloud contracted, it began to spin faster and faster, much like a figure skater pulling in their arms during a spin. This rotation caused the cloud to flatten into a disk, known as a protoplanetary disk, with most of the material concentrated in the center. The center of this disk grew denser and hotter as gravitational forces continued to compress the material. Eventually, the temperature and pressure at the core became high enough to ignite nuclear fusion, marking the birth of a new star. Our sun ignited, its brilliant light illuminating the surrounding disk and heralding a new era in the solar nebula. The remaining material, now bathed in the sun's energy, continued to swirl around the newborn star, setting the stage for the formation of planets.
The intense heat and solar wind from the young sun pushed lighter elements outward to the cooler regions of the disk. Meanwhile, heavier elements, unable to escape the sun's gravitational pull, remained closer to the center.
This separation of materials played a crucial role in the formation of different types of planets within our solar system. Rocky planets rich in metals and silicates formed in the inner regions where temperatures were higher. Farther out, in the cooler regions, gas giants composed mainly of hydrogen and helium began to take shape.
The early solar system was a chaotic and violent place, with frequent collisions and interactions between forming bodies. These collisions were not just destructive, they were also constructive, helping to build up the planets through a process known as accretion. This tumultuous period marked the beginning of the long and complex process of planet formation.
The sun's energy continued to bathe the swirling disk of dust and gas, driving chemical reactions and physical processes. This energy, along with the gravitational forces at play, would ultimately shape the destinies of the forming planets. The solar nebula was a dynamic and ever-changing environment, full of potential and promise. Particles within the nebula constantly collided and interacted, sticking together to form larger and larger bodies.
Gravity, the invisible hand of the cosmos, played a crucial role in shaping the nebula and guiding the formation of celestial bodies. It drew matter inward, leading to the formation of the sun and setting the stage for the birth of planets. The remaining material, now orbiting the young star, continued to evolve and coalesce. Over millions of years, this material would coalesce into the planets, moons, and other bodies that make up our solar system today.
Dust and ice particles within the solar nebula began to collide. They stuck together, forming larger clumps.
These clumps grew bigger over time. They became planetesimals, the building blocks of planets. Gravity played a crucial role in this process. It attracted smaller particles to larger ones. Planetesimals continued to attract more material. They grew larger and larger. Some planetesimals reached hundreds of kilometers in size. These larger planetesimals exerted even stronger gravitational pull. They attracted smaller planetesimals and dust. The process of accretion continued for millions of years. Planetesimals collided and merged. They formed protoplanets. These protoplanets were the precursors to the planets we know today. They were still hot and molten. Gravity shaped the orbits of these protoplanets. Some protoplanets collided with each other. Others were ejected from the solar system. The remaining protoplanets continued to grow. They eventually became the planets we see today. The early solar system was a chaotic place. Collisions were frequent and violent. Planetesimals constantly bombarded each other. This process led to the growth of protoplanets. Over time, the solar system became more ordered. The planets settled into their current orbits. Gravity was the driving force behind this evolution. It sculpted the solar system into its present form. The formation of planetesimals was a crucial step. It laid the foundation for the development of planets. Without planetesimals, our solar system would look very different.
Proto-Earth was a hot, molten ball, a seething mass of liquid rock and metal. It was constantly bombarded by planetesimals, the building blocks of planets which rained down from the chaotic early solar system. The impacts generated immense heat, enough to keep the surface in a molten state and prevent any solid crust from forming. This heat kept the planet in a molten state, a churning cauldron of liquid rock and metal. The early Earth was a hostile environment with temperatures soaring and a surface that was anything but stable. Heavier elements, like iron and nickel, sank towards the center. Driven by gravity in a process known as planetary differentiation, they formed the Earth's core, a dense metallic heart that would play a crucial role in the planet's future. Lighter elements, like silicon and oxygen, rose to the surface, creating a less dense outer layer. They formed the mantle and crust, the solid outer shell that would eventually support life. This process is called differentiation, a fundamental step in the evolution of terrestrial planets. It gave Earth its layered structure with a core, mantle, and crust, each playing a vital role in the planet's dynamics. The early Earth had no atmosphere, a barren, rocky world exposed to the harshness of space. It was constantly bombarded by asteroids and comets, which brought not only destruction but also essential ingredients for life. These impacts delivered water and other volatile compounds to the planet, seeding the early Earth with the building blocks of its future oceans and atmosphere. Over time, an atmosphere began to form, a thin veil of gases that would eventually thicken and protect the planet. The Proto-Earth was a dynamic and evolving world. It was constantly changing, shaped by both internal and external forces. The differentiation into core, mantle, and crust was a crucial step, setting the stage for the planet's geological activity. It set the stage for the development of plate tectonics and the formation of continents, the large land masses that would eventually host diverse ecosystems. Volcanic activity was rampant on the early Earth, with eruptions reshaping the landscape and releasing gases into the atmosphere. Volcanoes spewed gases into the atmosphere, contributing to its composition and helping to trap heat. These gases contributed to the formation of the early atmosphere, a crucial step in making the planet habitable. The composition of the early atmosphere was very different from today's atmosphere, rich in carbon dioxide, methane, and water vapor. It was rich in carbon dioxide, methane, and water vapor, creating a greenhouse effect that helped warm the planet. The early Earth was a hot and violent place with volcanic eruptions and meteor impacts, constantly reshaping its surface. It was constantly being reshaped by impacts and volcanic activity, a world in perpetual motion. The formation of the Earth's layers was a key event, laying the groundwork for the planet's future stability and habitability. It set the stage for the development of the planet's surface features, including mountains, valleys, and eventually oceans. The early Earth was a world in constant flux, a dynamic environment where change was the only constant. It was a world undergoing dramatic transformations, setting the stage for the complex and diverse planet we know today. Section 4, Lunogenesis, a cosmic collision. A Mars-sized object collided with the early Earth. This impact ejected a massive amount of debris into orbit. This debris coalesced to form the Moon. The impact was a cataclysmic event. It had a profound effect on the Earth. The impact tilted Earth's axis. This tilt gave us our seasons. It also stabilized Earth's rotation. This stability is essential for the development of life. The Moon's formation was a defining moment in Earth's history. The impact melted a significant portion of the Earth's surface. It also vaporized a large amount of the impactor. The debris from the impact formed a ring around the Earth. This ring eventually coalesced to form the Moon. The Moon's formation had a significant impact on Earth's evolution. It stabilized Earth's climate and rotation. It also created tides. The Moon's presence has played a crucial role in the development of life on Earth. The giant impact hypothesis is the most widely accepted explanation for the Moon's formation. It is supported by a wealth of evidence. The Moon's composition is similar to Earth's mantle. This suggests that the Moon formed from material ejected from Earth. The Moon's formation was a dramatic event. It was a pivotal moment in Earth's history. It shaped the Earth's future in many ways. The Moon's presence has had a profound influence on Earth's evolution. It has played a key role in making Earth the habitable planet we know today. Section 5. Cooling Earth, the oceans and atmosphere emerge. As Earth cooled, the molten surface began to solidify. The first rocks formed, marking the beginning of a new geological era. The Earth's crust began to take shape, driven by intense geological processes that would continue to mold the planet's surface. This was a crucial step in the planet's evolution, laying the foundation for future land masses and ecosystems. Water vapor in the atmosphere condensed, leading to the first rains. These rains fell for millennia, gradually filling basins and forming the early oceans. The first oceans were probably acidic, a stark contrast to the neutral waters we are familiar with today. They were rich in dissolved minerals, which would play a crucial role in the chemical processes that led to the emergence of life. Volcanic eruptions were frequent, releasing a variety of gases into the atmosphere. These gases included water vapor, carbon dioxide, and nitrogen, creating a thick and hazy atmosphere. The early atmosphere was very different from today's atmosphere, lacking the oxygen that is so vital for most modern life forms. The cooling of Earth was a slow process, taking millions of years to reach a stable state. It took millions of years for the planet to cool sufficiently to support the formation of stable land masses and bodies of water. The formation of oceans and the atmosphere were critical steps in the development of life, providing the necessary conditions for biological processes to begin. The early oceans were hot and acidic, a far cry from the life-supporting waters we know today. They were a far cry from the oceans we know today, teeming with life and supporting diverse ecosystems. The atmosphere was thick and toxic, filled with gases that would be deadly to modern humans. It was not breathable by humans, lacking the oxygen that we depend on for survival. Despite the harsh conditions, the early Earth was teeming with potential, setting the stage for the complex life forms that would eventually emerge. The formation of oceans and the atmosphere created the conditions necessary for life to emerge, providing water and a stable environment. The stage was set for the next chapter in Earth's story, where simple life forms would begin to evolve and diversify. The cooling of the Earth's surface allowed for the formation of the first continents, which would become the building blocks of future ecosystems. These early land masses were very different from the continents we know today, constantly shifting and changing due to volcanic and tectonic activity. They were constantly being reshaped by volcanic activity and tectonic forces, creating a dynamic and ever-changing landscape. The formation of oceans and continents was a crucial step in Earth's evolution, setting the stage for the development of complex life forms. It set the stage for the development of life, providing the necessary conditions for biological evolution to take place. The early Earth was a dynamic and ever-changing world, full of geological activity and potential for life. It was a world ripe with possibility, ready to give rise to the diverse life forms that would eventually inhabit the planet.